Welcome to 6-5, the second fundamental theorem of calculus integration involving the natural log function. You know this isn't how I teach this. I taught it in class. I'll always teach it in class. If I forget, then please, students, remind me to go through this first before we do it this way. We always use the Khan Academy here. Now, why? That's because this lecture is quite esoteric in its nature. And remember, what I've been teaching you is that the integral of the derivative of a function is the original function. And specifically, I've been teaching you that if you have a definite integral from a to b of the derivative of some function, that, and this is, by the way, this is conceptual, but this is actually the fundamental theorem of calculus. I guess we should call it part one, part one. What I'm about to do is part two. All right, so this is part one, and we've gone over it, definite integral, great. This is part two, where we have this esoteric, like this weird thing where we're like, okay, what happened? Now all of a sudden there's t's. What happened to all my favorite x's? Okay, well then just try to plug that x in. You know what I mean? So the integral of a derivative should be the original function, right? There's my original function, and I would normally say plus c, but this time we're going to evaluate it from 10 to x. And what I'm saying is I'm doing this thing right here, and I'm saying that that's my lower bound and that's my upper bound, and so I have f of t minus f of, sorry, what variable are we using? My bad, x. F of x minus f of 10. And you're like, where did the x come from? It's my upper bound. It's my upper bound. I was trying to give it to you. I meant to write it down right there. That'll actually probably be the most common student mistake, is to forget to change the variable. That's what this formula is. This is a change of variable formula. It just tells you to put x's everywhere that you saw t's before. Okay, so then let me try it this way. I have exactly the same thing before, so f of x minus f of 10 is my answer, but now I have this dx encapsulating all of it, meaning, could you please take the derivative of that little piece? Okay, sure, the derivative of f of x is f prime of x, and the derivative of 10 is 0. So it means that this lower boundary just disappeared. This disappears. Why did it disappear? Because I took the derivative of it. So now this is his way of introducing to you the fundamental theorem of calculus, which says that if you had a function of f of t, you could just change it into a function of f of x. That's it. Boom. That's it. So anytime you have any kind of problem, so let me do in one more, dx of, the integral of pi all the way up to, theta of sine of x, 2x plus 3 dx. I am just going to massively change that. Remember, this here is a variable, and this here is a constant. And so I can just do this. Ready? The sine of 2 theta minus plus 3 is going to be my answer. I just change, and I don't have to worry about the pi because this part disappears. And I showed you why and how in class. We discover this in a little bit more deeper way, okay, and when we do it in class. So let's do it with just, like I said, mostly notation. It feels kind of esoteric, kind of weird, but let's see if we can't get through it. So how do I do this? Remember, these two things just sort of cancel out. The only thing that's weird here, actually, is that wait, oh, my bad. Oh. Now I want to do this one. The only thing that's weird here is that x is in the bottom and that 0 is on the top, which means that I am subtracting the f of x piece. So I have a 2x minus 3, but I need a minus sign in front of it because I have, remember how I have f of b minus f of a? Well, because, because b is normally on top, well, that means that I have 0, because this was a 0, and now I will minus f of x. So there you go. That's the answer to that one. All right, so I'm coming back up to number 3 now. Sorry about that. Okay, so this one then, I want to plug in that this is f of x squared, and, well, hold on. I don't want to plug it in right away. Hold on. I want to do it like this. I'm going to evaluate it from 0 to x squared, and so that means I'm going to plug it in the following f of x squared minus f of 0. Okay, yeah. And then there was no ddx out here, right? So it wasn't here. We were just doing the integral. Okay, so now what does he do? Obviously, he's going to throw the ddx, and we're expecting these two things to kind of cancel out, right? So what am I supposed to do? I did this piece, and what I got was f of x squared minus f of 0. And then I am supposed to really take the derivative of that. And so what I will get is I will get f of x squared with a prime mark here, but don't forget that I am going to take the derivative of the inside function. This f of x squared is a composition of f of x and x squared, where I plugged x squared in to my function. So that's my inside. This is my inside, and that is my outside. I don't know what it is, I mean, is it sine or is it natural log or whatever, I'm wrapping x squared inside of that function. All right, so then here the derivative of a constant would be 0, right? If I do the derivative of f of x squared, then it looks like this. That's my chain rule. This right here, this is my chain rule hook-on piece. And then that is a constant. So, boom. So what will my answer be? It will be 2x f prime of x squared. All right, you might be dying to see like what this function looks like now. You know what I mean? And I feel you. Let me try one more, and then I'll see if I can't give you an example with an actual function in it. All right, so f of x is supposed to be my answer, and I'm supposed to evaluate it from x cubed to 2x, and that means that neither one of these things are constants. Neither one of these things are going to disappear. I'm going to get f evaluated at 2x, and I'm going to subtract f evaluated at x cubed. And I'm loving this because obviously we did not have anything out here before, so he's going to throw it out there now. And this little piece that I just figured out is this little piece right here, so I'm going to say I need to do a ddx on that f of x, on that f of 2x, and this f of x cubed, and boom. I'm really focusing on this notation because you're going to find it useful during the AP exam, I promise, okay? I'm just telling you. All right, so f prime of 2x, and then a ddx on the 2x minus f prime of x cubed with a ddx of x cubed, meaning that I'm using my chain rule. There's my chain rule hook on pieces. So my answer is going to be f prime of 2x with a 2 in front of it, because the derivative of 2x is 2, and then minus, well, let's go ahead and do the chain rule hook on piece now, and then f prime of x cubed would be my answer, okay? Like, well, how does this actually play out? It turns out, I just did this one was negative, so it felt a little funny. But number 8, hopefully, oh, wait, this one's also kind of funny because those are both constants, so I just get 0. And then how about here? Does this one seem a little more straightforward to you? Let's try it. Oh, so we get x cubed being squared plus 2 times x cubed, and this whole thing we need to do that chain rule hook-on piece. The derivative of x cubed is going to be 3x squared. And I know you want to simplify that, but I want to leave it in the format where you could see that all I have to do is substitute this in and then multiply by the chain rule. Hook-on piece. How about this next one then? So I would say that f prime of x is going to be 1 minus t squared, the whole thing being taken to the 10th power. And what am I plugging in? Is this 3x squared? And don't forget to take the derivative. The derivative of 3x squared is 6x. So this all will be multiplied by 6x. Like, is it really that easy? Yeah, it's really that easy if you just remember to do the chain rule hook-on piece. Don't forget the hook-on. And then proving it, like I feel like I've already done that in class, right? Now this next piece might feel like he's changing topics, but he's really not. He's saying differentiation and integration are inverse operations. So when you take the derivative of the natural log of x, you get 1 over x. Okay, that means that when you do the integral of 1 over x, you should get the natural log of x. And notice how I'm ignoring the fact that there's an absolute value there. I think you can ignore it too in the most for the most part. You'll see it in the multiple choice answers, and you just, you accept that it's there. If this turns into a problem where it's free response and you accidentally don't put absolute values there, they won't ding you. They don't mind, okay? In most cases, it doesn't matter. It's just in a few cases where it does, and they've decided to not grade you on that portion of the exam. They're not stressing you out with those absolute value symbols. So then here we'll mention that if this was just x, then I get 1 over x. But over here, when I do the derivative, when there's a function in there, when this is a composition of functions, and this is my inside function, then I will get that 1 over x, but then that would be multiplied by the chain rule hook-on piece. All right, so there, I'm going to write this down. Here you go. So 1 over x times dx, right? I took the derivative of something. So I'm saying that what if I had like u was like 2x plus 4 plus 5. Let's make it not factorable. All right, so I would get 2x plus 5 in the denominator, but then I would have to multiply by the chain rule hook-on piece. Du is going to be 2. And so I'm saying that there should be a 2 here. And so we write it like this, 2 over 2x plus 5. And no, these 2's do not cancel out. Oh my gosh, stop asking me that. Seriously, they do not cancel out. You have to factor a 2 out of the bottom. If you were dying to factor that 2 out, it would look like this. This is x plus 5 halves. Now you can cancel out the 2's if you wanted to. You could say you have 1 over x plus 5 halves. And only nobody likes that when you do that. It doesn't make them happy to have a fraction in the denominator, okay? So anyway, what I'm trying to say is that this is 1 over u, and this is du, and that's what he's saying. Now is that, boom, let's do du over u, which is literally how I asked you to memorize it, okay? I just want you to know that du over u is the same thing as 1 over u times du, okay? That's how he has his, is like that, and this is how you have it in your head, all right? And notice that you can take the derivative and get get u prime over u, or if you do the integral of u prime over u, you should just get the natural log of u. So he's just reminding you of all that stuff. So although it is true that both the natural log of x equals 1 over x and the derivative of the absolute value of the natural log is also equal to 1 over x, the integral of 1 over x dx is only with the absolute value. Why? The domain of natural log of x is restricted. Remember, it's x is got to be greater than or equal to 0. That's a requirement of the domain of the natural log of x. All right, and I'm saying again that I don't stress about it. All right, so what is this then? I'm going to say that this is just this. Ready? It's -3 times 1 over x dx. And that -3 can be thrown out in front. And so this is 1 over x dx. And we just went over the fact that that is the natural log, the absolute value of x. And then plus c, right? Okay. So what about this one then? Well, we're doing a different variable, but I'm saying that this is the bottom and this is that chain rule hook-on piece. And so I'm thinking about it like this, that u is p squared plus 1, and that when I do a derivative of this, I should get a 2p, right? And then a dp. So when I do a u substitution then, I'm missing a 2, right? So if I put this here and I put this here, then I've taken care of that. And so this will, the integral will be 1/2, and this is the natural log, ready, of p squared plus 1 with an absolute value and a plus c. Okay. How about the next one? Let me put the answer down here. So the derivative, the d dx of tangent is equal to secant squared x. So, that's my chain rule hook-on piece. And so the answer should be the natural log of the absolute value of tangent of x plus c. Okay. That was too easy. 14 and 15 must be a little bit more complicated. Let's take a look. Integrate that. Oh, that's funny. I was talking to somebody about this one. Okay, this is the integral already of 1 over x times the natural log of x. How is it possible that I have a natural log of x in here as my chain rule hook-on piece? What I take the derivative of and I still had a natural log, there must have been 2 of them. Think about it like this. d dx of the natural log of x being squared would end up giving me a 2 times the natural log of x times, ready, the derivative of the inside piece. This piece, I have to take the derivative. The derivative, that will be 1 over x. So that would give me 2 natural log of x over x. Yeah, I'm missing a 2. You can see that I'm missing a 2. So I'm just saying that we should make sure that we have one for ourselves. Here, let's do this as a u substitution, right? Like as a kind of like a u substitution. So we say that u equals the natural log of x, and therefore du will be 1 over x dx, meaning that dx will be x times du. So I want to make this u substitution, and I'm saying that I have the integral, ready, of what was u again? It was natural log of x. Okay, so I have u, and then I have a 1 over x. I'm not ready to make that substitution yet. And then dx was x du, and these guys canceled out. And so I have the integral of u du, which is going to be what? It's going to be u squared over 2 and plus a c, except I have to plug back in what u was. So this is natural log of x being squared over 2 plus c. That one hurts your brain. You should try and do it again without watching the video, without taking notes. If you can do this one from top to bottom, it'll never confuse you again. You just need to do it like 3 or 4 times in a row and you'll have it knocked out. All right, same thing's happening over here. I'm just saying that u equals 2 minus the natural log of x, and so du equals 1 over x dx, and make that negative, please. And then I'm going to multiply by x on both sides, so dx will equal negative x du, okay? And so then I'm going to plug I'm going to say that this is really the integral of 1 over x times, ready, 1 over u cubed, and dx is a negative x is a negative x du. And this x and that x cancels out, so I have a negative in front, and this is a u to the negative 3 power and a du. Right now I'm trying to figure out that integral. My bad. Trying to figure out that integral. And so what am I going to do? I'm going to say that this is u to the negative 2 divided by negative 2 with a negative sign out in front because I'm bringing that down, and then plus c. And I'm going to have to put that u back in here. So by the way, a negative and a negative makes a positive. So there's a 1/2, and this is 2 minus the natural log of x, and plus, and that's to the negative 2 power, and that's plus c. And you can leave it like that, or if you're feeling really compulsive about it, you can say this is 1 over 2 times 2 minus the natural log of x squared plus c. And that's your final answer on that one, okay? So these next two examples are pretty quick because cotangent is really the same thing as cosine over sine. So the integral of cosine of x over sine of x and a dx here means that I can just say that this is u prime over u. You know what I mean? Like the derivative of sine is cosine, and so I'm feeling really good about my answer being the natural log of the sine of x plus c. And if you wanted me to show more steps, bring it to me in class. I'd be happy to go over it more steps. Same thing here, by the way, is that tangent is the same thing as sine of x over cosine of x and a dx. But keep in mind that the derivative of cosine, dx of cosine of x, is going to be negative sine of x. So I'm technically missing a minus sign right here. So let me throw two of them out there, so that way this is in my u prime u form, and I can see now that it will be negative natural log of cosine of x plus c. And I guess we just have one little more piece to do here. I would say that we just did this one, and that one looks extremely similar. The only thing that I'm missing here is that there should be a derivative of 2x somewhere, right? I'd like it to be right here in front. And then it'll be a straight, path back to my antiderivative. So I'm going to throw that 1/2 out in front and the 2 in front, and remember how those two things are equivalent to 1. So I'm throwing together an answer here, and I'm using this guy, right? Because I'm saying that this is negative natural log, the absolute value of cosine of 2x and plus a c. And oops, with a 1/2 in front. Sorry about that. And that's my answer. And you're like, can it really be that easy? Sure. Take more time and try this method with the 2x in there, and I guarantee you that if you do it correctly, this is what you're going to get. Good luck on the homework.